So yeah, I'm Michael, and today I want to talk about our project LingoDB, an open compilation and optimization framework for sustainable data processing. And I want to start with two major challenges that you face basically when you want to build a new system today. And the first one is diverse workloads. So today it's not just enough if you have support for SQL, but you want more. You want the users to be able to extend the system with user-defined functions, user-defined operators, but also have the capabilities for graph analytics, data mining, machine learning, process mining, and so on. So a lot of domains that are a bit different, but all in the sense around data processing. And then on the other hand, we have modern hardware, which unfortunately is not that simple anymore. So you don't just have a single CPU core, but a lot of cores. There's heterogeneous hardware with GPUs, FPGAs, smart NICs, smart storage, and so on. And also going into cloud, you maybe want to be distributed and want to deal with a distributed environment. If we dive in a bit more with diverse workloads, what do we want? Well, in the ideal case, we want like a white box integration of other domains. So in the ideal case, we want to bring just any domain and treat it like if somebody wrote native C++, for example. So no overhead, maybe even logical optimizations. We also want to automatically profit from available hardware, like use multi-threading, offload it to GPUs and so on. And also have, user-defined operators, user-defined algorithms that are just working as if it was written in the engine. For example, if we have like a PyTorch linear regression model, and we would like to use it as a predicate in a SQL query, like we as humans can see that this is just equivalent to a comparison with a constant that the query optimizer could then just push down to a table scan, and it can be executed efficiently, right? And I mean, this is what we would want from a modern query engine as well. Yeah, the reality is that we don't get it. So we get usually a black box integration, which comes with high overhead. You can't do really logical optimizations, and you don't automatically profit from, for example, multi-threading. Again, with like PyTorch as an example, you usually just embed a Python and just run it with Python, and it works, but it's of course a lot slower. For the hardware, again, what do we want? Yeah, in the best case, hardware could be mostly treated like as a magic black box that just works. You just formulate operators or algorithm in a mostly hardware agnostic way, and then the query engine automatically adapts these algorithms for the available hardware, and magically it just runs. If, for example, if you think about a hash join, the ideal case would be if you just say, oh, I want to build a map over these values, over these tuples, and then later I want to probe them, please do it some way. And the query engine will do this, for example, with employing autopolarization and just distribute it across CPU cores. But the reality is that, unfortunately, the hardware cannot be treated as black box. And engines are also developed regarding typically one execution model. So if you are targeting CPUs, it's usually very difficult to just then go to GPUs. And this also means that operators and algorithms are manually adapted by the developers of the database engine to the target hardware, to the target environment. For the hash join, this then means you have to care if you are targeting multi-core CPU environments, you have to care about thread local states, do some parallel stuff, and care about all the small details, which requires a high expertise and is very cumbersome. So the main question is now, why don't we get what we kind of want? And the main answer is, like, query engines are very complex, consist of very complex monolithic parts. This just makes it very difficult. So typically we start with some logical plan that comes from somewhere, for example, from semantic analysis. And then there's the query optimizer, again, as typically a very complex part that takes in the logical plan, does a lot of magic voodoo, and finally a physical plan is produced that's then fed into some kind of query execution engine that's uses some compiled approach or a vectorized or some other form, but still typically very complex, very monolithic. The bad news is that when you want to integrate something, for example, PyTorch or something else, you have to go through a whole stack. And this means that you have to have knowledge for every part. And as these are very complex, it's not easy. What our approach is basically we break up these monolithic components that we just shown and break them down into much more smaller things. So we start by not having like a single query plan, but more having like open intermediate representations that are just a bundle of intermediate representations that can be freely combined with basically any intermediate representation for machine learning from whatever other domains, and you can just stack them all together, and then you have some kind of query plan by stacking them together. The next step is that query optimization is not like a monolithic component anymore, but is executed through a set of compiler passes. And this means that you can just interleave any other pass, for example, also passes that perform simplifications or optimizations for other domains. And then by combining them and interleaving them freely, you can really make cross-domain optimization feasible. The third step is then a layered query execution. So we split the execution phase into multiple layers, and we lower the initial IRs step by step until we reach some low-level IR, for example, LLVM. And again, this is not totally new. There's prior work by Shaker et al. With DPLab and so on. But the nice thing is you can just add in your custom lowerings for custom intermediate representation. So for example, if we again go back to the PyTorch example, you can just add in a new intermediate representation into the mix, then interleave some simplification paths with traditional query optimization steps like join ordering. And then later we can just add a new torch lowering path that lowers representations of torch to some, for example, arithmetic expressions that we know how to execute. Well, at first this seems like a nice idea, but it also sounds like a very lot of work because you're basically throwing away all the stuff that's already there and building your own kind of query engine. Fortunately, the machine learning community had similar problems. So they have a lot of front-end representations. Basically, every framework has their own ideas for the front-end side, and they have a lot of heterogeneous hardware, starting with CPUs, but especially GPUs, TPUs, and so on. And to solve this, they basically came up with MLAR, which is a meta-compiler framework that supports mixing and also hierarchies of intermediate representations. And the idea is that it's like a common framework, a common ground, a common intermediate representation format, which enables you to bring your own dialect, your own intermediate representation as a dialect in this framework. And such a dialect consists of a type system and operations on it. You can have compiler passes and lowerings to other dialects. And the good thing is that this matches quite closely what we are after. And therefore we also added new dialects basically for query processing. And if we now start look at this SQL query, we can translate it one-to-one to our new MLAR dialects. This then looks like this. So you have some more high-level declarative operations that correspond to relational operators, like having base table operators and cross product and selection and materialize. And yeah, you also have like scalar operations for expressing predicates and so on. And this allows you to really just mix and match with all the other dialects in the MLAR ecosystem. And yeah, it's quite expressible. Once you have this, the next step is, of course, query optimization, as I said, with compiler passes in the MLAR framework. And while this sounds a bit unorthodox at first, it really works quite nice. So we implemented all the standard stuff for query optimization as compiler passes that are executed one after another. So we start with some simplification steps, applying some rewrite patterns. Then we decorrelate queries, unlist correlated subqueries, and so on. Then we split operators and push them down or reorder them more generally. We then perform join ordering with like state-of-the-art algorithms, and then we have a physical optimization phase that basically annotates each operator with an implementation variant. And again, the nice thing is, as we are in this MLAR ecosystem, you can already reuse existing MLAR passes like common sub-expression elimination, and also reuse a lot of other stuff like dead code elimination, constant folding, simplification, and so on. So after query optimization, we want to execute or implement relational operators. And the bad thing is that just having this declarative IR for relational algebra is not enough, in our opinion. So you still have relational operators, and implementing them is super hard, even harder if you have to do it for a certain hardware. And in addition, extending it from the outside is still very difficult, because either you have like relational operators, very high level, very declarative, or you basically have to fall back to imperative code that you can do because you are in this MLAR framework, but it's still not trivial to do. This is why we came up with like a declarative suboperator layer below relational algebra. It's again one of these layers that I've just shown, and it serves basically three purposes. The first one is that it's exposed to the outside, so everybody or any user can use this layer and for expressing user-defined operators and algorithms, still in some kind of declarative way. The second purpose is that we can implement relational operators with them, very kind of decouple the semantic implementation from some imperative implementation. And the third thing that we can do is now can apply automatic transformations, automatic optimizations on this level, especially for modern hardware. So how does this kind of look like? The first thing is that most importantly, we want to be able to embed them into basically relational operator trees. So we also want them to use a related concept like using tuple streams for kind of connecting them. Then we also have or made state explicit. So you have to access state explicitly. And there are different control flow concepts. Also, for example, you can express iterative algorithms, now very efficient. And that's basically the overall idea. So how does this work for now a relational query? We start with the query on the left with an outer join. We first basically translate every relational operator into a suboperator plan node for node, which then looks like this. And because we have a lot of very small, simple suboperators, we can just translate them to imperative code with very small templates. You just have basically a template of code for each suboperator, and using that we can get very efficient code that is in this data-centric manner. And then in between, we have the potential for optimization. So for example, we can reuse state, delay some loading and so on. So there is some optimization potential. And in addition, we can also do adaptations to the hardware we want to run on. So most importantly is, of course, autopolarization. So we start with like model-driven parallelism. I mean, that's super effective, but it also comes with a high effort for the developers, right? You have to adapt every single operator, and this is a lot of work. Our idea is that with this new layer, we can do this automatically. We just have, a pass that automatically rewrites such sub-operator programs so that they can be safely executed, and we can automatically parallelize them. The strategy is that we first detect all the conflicts, so read, write, read, and write. And we can do this quite easily because state is explicit and state accesses are also explicit. So we really know where conflicts are. And then we basically try to avoid conflicts by either using thread local states, marking operations as atomic, or in the worst case, introduce some small locks. And for a quite simple aggregation, we can look at this. So if we scan, for example, a base table, we have a map that could be a hash map. And then for each tuple that comes out of the scan, we first perform a lookup in the map. And if no entry exists, we then perform an insert based on the pointer to the element in this map. We then perform a reduction, for example, summation. And then after this pipeline is done, we scan the map which contains the results. And this is basically the aggregation. What you can now do is we detect conflicts and use the first strategy, where we then rewrite the map to be thread local. And after the pipeline, we then merge everything together into a nice global map. And we can do this automatically. So putting it all together, how does LingoDB look like? So we start with basically SQL, or combined with user-defined functions, user-defined operators. We then parse everything and create an MLAR module out of it that mostly consists of relational operators with this rel dialect and scalar expressions that are usually from this DB dialect. And of course, if you use concepts like user-defined operators, you also might have some sub-operators. Then we just perform query optimization on this module using a lot of parses. And the nice thing is that we can also exploit things. For example, if you do a user-defined user-defined operator, the query optimizer can basically analyze it and potentially also push things through it, for example, predicates. After the query optimization is done, the relational operators are lowered to, or translated into sub-operators. Again, on this layer, we then perform further optimizations, but most importantly, also autopolarization. Then we translate the sub-operators to imperative code, as we had seen before with the templates. And then we have like imperative MLAR modules that are further lowered until we reach some kind of low-level IR, in this case LLVM, that then generates efficient machine code that calls into our runtime that's based on Apache Arrow. And this all works quite nicely. We get a huge support for all of different SQL operators, all the basic ones. We have set operations, we've set a multi-set semantics, a lot of different joins, types, join variants, also complex aggregations, also window functions, and used operators like group join or top K for optimization. With all of this, we can not only run tpch, but also every tpcds query. And on top of like the core SQL functionality, we, as I said, users can basically build user-defined operators by nesting sub-operators. Now, again, going back to the PyTorch example, how would this look like? Well, you would start by having some PyTorch code. Then you need to somehow translate this to MLAR, to the MLAR part of PyTorch. The good thing is that this is already done, so we can translate this and at some stage just apply the also existing lowerings for the Torch dialects. And the nice thing is that by adding in some and interleaving special passes for the Torch dialect, we can get cross-domain optimization through interleaving passes with good optimization. So I just showed you it. It's kind of working, but what's about the performance? Well, before I show you the number, let's just say the whole project is not about the performance as the primary goal. It's like flexibility and extendability is the most important thing. Then comes performance, but in our performance is very important. So if you look at TPCH and we compare it with DuckDB and the other two systems developed at TUM, Hyper and Umbra, what you can basically see is DuckDB is a bit slower, Hyper is more or less on par with LingoDB, and Umbra is still a bit faster. For TPCDS, mostly similar, DuckDB a bit slower, Hyper and LingoDB on par, Umbra again a bit faster. Of course, these are execution times and compilation times are excluded, but at least with our approach, they're reasonably low. It's like not minutes or so, it's 50 milliseconds around. And this can, of course, be further reduced with other, using other backends for compilation, but also by caching and so on. But this is just orthogonal work. Nice thing is that we do not only have support for SQL, but we can do other stuff too. So for example, if we start with a similarity join, we once implemented it with DuckDB and Python, and already the DuckDB part takes a bit of time, but then the Python part takes even longer. If you just do everything with LingoDB by using the sub operators for the similarity join, it's a lot faster. And if we can then further exploit predicates that we can push through the user-defined operator, performance gets even better. You can also support iterative algorithms like k-means and PageRank, again, by just using the sub-operators integrated into relational queries. What you can see is if we do the whole thing in Hyper using recursive SQL, it's quite slow. I mean, it's faster than a lot of the alternatives, but not that fast. Then if you use basically the Python standard packages, they are usually quite fast, but if you have to build up, for example, a graph representation first, that also takes some time. By just using the sub-operators together with basically SQL, it's much faster with LingoDB. The whole project works quite well. It's also quite accessible, but there's still a lot of work to do. So going back to the diverse workloads, I mean, we have the sub-operators that can be used to extend the engine from the outside, but it's still can be much more user-friendly. We also want to build front ends for different domains like graph processing, data mining, machine learning, and so on. And then once this is there, we really want to get into this cross-domain optimizations topic more. For modern hardware, again, we already have autopolarization, but there's auto-vectorization that we could also do very similar. Auto distribution could also be a thing. And of course, regarding heterogeneous hardware, we want to offload things to GPUs when it makes sense. And regarding compilation times, but also in general, we want to get much more adaptive. So we want to adapt to if some pipeline is running longer, we might want to recompile it with more optimizations. If something unexpected happens, we also want to react to it. So getting the whole thing more adaptive. So all in all, with LingoDB, we try to go novel ways, especially by breaking up the traditional components. So instead of a query plan, we have these open intermediate representations where you can just bring your own domain-specific IRs. Then query optimization is done with compiler parsers, where you can, again, just bring your own custom parsers, interleave it, and get cross-domain optimization. We then introduced declarative suboperators. So they are there to, on the one hand, reduce complexity, but we also get automatic optimizations, especially autopolarization. And you can basically compose your own fancy user-defined operator. Finally, we have layered query compilation with a quite high flexibility regarding execution environments, execution backends, which also makes it a lot easier to target heterogeneous hardware. Yeah, in the end, this whole project is open source. You can just go to GitHub, check it out. We have a website, especially also with a web interface where you can try all the standard SQL queries. And we also have a Python package that you also can try out, also in process, similar to DuckDB. And yeah, so you can just try it out, play a bit with it. Yeah, thank you.